Hello everyone, welcome. Today we're going to talk about element number 41, Niobium. Niobe was the daughter of Tantalus, son of Zeus. Look at a periodic table and you will find her element, Niobium, just above tantalum, element number 73. Sadly, the element below tantalum is not named cesium. It was named dubnium, element 105 in 1997 after much argument, none of which included a proposal to call it cesium. Evidence that familiarity with the classics is no longer considered essential to a well-rounded education. Niobe mourned the loss of her children, who were killed by Artemis and Apollo, while the author mourns for the loss of his samples of niobium, which were confiscated by the FBI. He had assumed they were part of an obsolete missile part, a rocket engine with a niobium superalloy nozzle. According to the author, you can never tell what you're going to find on eBay. Rocket nozzles are made of niobium alloys because they resist corrosion even at high temperatures. Niobium is also commonly used in jewelry and coins because it can be beautifully anodized, forming a rainbow of colors through the indifference of light diffracted off thin transparent layers of oxide on its surface. Corrosion resistance, beautiful colors, and an evocative name combine to make niobium the ideal metal for body piercings. This makes it surprisingly easy to buy pure niobium in shopping malls if you aren't too embarrassed to go into that kind of store. If one of those piercings goes wrong, you might find yourself surrounded by a far larger quantity of niobium. Coils of niobium titanium superconducting wire are used to create huge magnetic fields inside MRI, magnetic resonance imaging machines found in hospitals, which among other things can be used to locate objects lost inside the body. Body scanners. Doctors can see into the body using body scanners. These can produce images of internal organs, locating defects and diseases. Some scanners work by passing X-rays or gamma rays through the body. The most useful scanner is an MRI, magnetic resonance imaging scanner, which works with nuclear magnetic resonance or NMR. Inside, the patient is bombarded by a strong magnetic field and then by pulses of radio waves. These are harmless, unlike X-rays and gamma rays. The nuclei in the body's atoms produce magnetic signals that detectors pick up, and a computer forms an image from these. Inside a body scanner. The patient enters the scanner on a sliding couch below. Inside, he or she is surrounded by curved panels that contain the coils that produce the radio pulses and NMR signals. Around the panels are ring-shaped electromagnets which may be made superconducting by cooling them with liquid helium, even colder than liquid nitrogen. Scanning gives no sensation, not even a tingle. How the scanner works. Atomic nuclei each have their own tiny magnetic field. The scanner applies a strong magnetic field to line up the nuclear fields in the body's atoms. Coils then send out a pulse of radio waves which make the nuclear fields rotate. The rotating fields introduce electric signals in the scanner coils, which are built up by a computer into an image showing the distribution of the atoms of certain elements. As the amount of these elements vary from one part of the body to another, an image of the internal organs is produced. This was extracted from the medicine book, Seeing Inside the Body, MRI and Medical Scanning. In 1938, Polish-American physicist Israel Rabbi discovers nuclear magnetic resonance, the basis for MRI. In 1951, Robert Galbernard, using varying magnetic fields to locate the origin of radio waves emitted by the nuclei of atoms. In 1956, David Cole builds a device for tracking radioactive isotopes in the human body. And here we have after. In 1975, the first PET scanner goes live at Washington University in St. Louis. In 1977, Peter Mansfield invents the echoplanar technique to speed up MRI scanning. And in 2018, scientists in New Zealand developed the first 3D color medical scanner. Here we have another summary. With the help of titanium and niobium to create the magnets, hydrogen is one of the most abundant elements in the human body. The nuclei of hydrogen atoms are like tiny magnets. You might wonder, where does the hydrogen come from? Well, our body consists mostly of water, carbohydrates, and fats. Water is made out of hydrogen and oxygen, oxidized hydrogen. Fats are made out of carbon and hydrogen, hydrogen combined with carbon. And carbohydrates are made out of carbon, hydrogen, and oxygen, also known as sugars. There's the hydrogen. An MRI scanner produces a magnetic field causing the nuclei of hydrogen to align. It then uses radio waves to knock them out of alignment. When the radio waves are turned off, the nuclei realign and send out radio signals. By measuring these radio signals, the scanner's computer can create a detailed image of the body part being examined. MRI allows doctors to view the brain in slices of 0.04 through 0.16 inches, 1 through 4 millimeters. False color can be added to highlight particular features. From now on, I'll stop saying quote-unquote if they have quotation marks, but just know that I'm still referring to quote-unquote if it does have quotation marks. Here we have some information on niobium. We'll talk more about this later. So what happened to Niobe in Greek mythology? According to Homer's Iliad, Niobe had 6 sons and 6 daughters, and boasted of her progenitive superiority to the Titan Leto, who had only 2 children, the twin deities Apollo and Artemis. As punishment for her pride, Apollo killed all Niobe's sons, and Artemis killed all her daughters. Who is Niobe the daughter of? The tragic tale of Niobe is one of the most poignant in Greek mythology. Her father was Tantalus, king of a town above Mount Sipylus in Anatolia, but we do not know exactly who her mother was. Niobe had 2 brothers, Proteus and Pelops, who would later be a legendary hero and would give his name to Peloponnese. Niobe, in Greek mythology, the daughter of Tantalus, king of Sipylus in Lydia, and the wife of King Amphion of Thebes. She was the prototype of the bereaved mother weeping for the loss of her children. Is niobium better than titanium? Although titanium is even more corrosion resistant than niobium, niobium is lower priced and even more highly available. It's also one of the most inert metals, making niobium an ideal hypoallergenic body jewelry material for those who have more sensitive skin. Is niobium more expensive than silver? In addition, titanium and niobium can be put through an anodizing process, resulting in varying colors of jewelry without the toxic inks or dyes. It is slightly more expensive than sterling silver to buy in sheet, wire, and tubing form. Is niobium safe to wear? Because niobium is an inert element, most people with metal allergies can safely wear niobium. It's highly resistant to corrosion and other reactions, and is used in medical implants. By definition, niobium does not contain lead, nickel, cadmium, or anything else. It's just niobium. What is superconductivity? Superconductivity is a set of physical properties observed in certain materials where electrical resistance vanishes and magnetic flux fields are expelled from the material. Any material exhibiting these properties is a superconductor. Next in line, molybdenum, if you're interested in learning about the element, I'll leave a link in the description below, shares many of the strengths of niobium, but none of its romantic qualities. Here, directly from the book, we have an image of a high purity crystal niobium bar. Here we have 5 nines, 99.999% pure niobium crystal ribbon from the former Soviet Union. Here we have the mineral pyrochlorite, consisting of the element calcium, sodium, niobium, oxygen, hydrogen, and fluorine. If you're interested in learning about the elements, you can check out the link below, or you can check out my channel. I have made videos for calcium, sodium, oxygen, hydrogen, and fluorine. I will remaster the original videos. Other than that, let's continue. Here we have an image of a pattern-folded Damascus steel knife with interfolded niobium and copper handle. Sharp. Got cut just by looking at it. Here we have an image of a niobium alloy rocket engine nozzle, which, according to the author, was confiscated by the FBI. Here we have an image of niobium, which can be anodized to a lovely range of colors. Here we have an image of a niobium captive ring barbell for piercing one part of the body or another. Niobium resists corrosion even at high temperatures. If you're interested in simulating flying planes like in the Air Force, you can play the game Command the Stack. It is on Google Play and on the App Store if you're interested in downloading it. Niobium connects to the Air Force because it's used to make materials that the Air Force utilizes for flight and various other purposes. Speaking of uses, let's talk about niobium's uses today. Niobium, element number 41, the transition elements. Symbol Nb, atomic number 41, atomic weight 92.906. Its color is gray-white. Its standard state is solid at 25 degrees Celsius or 77 degrees Fahrenheit. Its classification is metallic. It is located right here. I'm named after the Greek goddess Niobe, daughter of Tantalus, and bear quite a likeness to tantalum. I am a pretty metal with a wild blue, green, yellow, purple, and violet oxides. I like to play it cool and don't easily get involved in chemistry, but you'll see me winking at you occasionally from belly piercings and in super alloys used in rockets. Niobium's date of discovery was in 1801. Its density is 8.57 grams per centimeters cubed. Its melting point is 2,477 degrees Celsius or 4,491 degrees Fahrenheit. Its boiling point is 4,744 degrees Celsius or 8,571 degrees Fahrenheit. Here we have the state of the world in 1801. Here's 1801. Here we have the Spanish colony. Here we have the regions that the French colonized, the British and America. This is North America in 1801. This is Europe in 1801. This is Southeast Asia and parts of Africa in 1801. This is South America in 1801. This is China and parts of Russia in 1801. And here's an overall map of 1801. Navel piercing. A navel piercing is a type of piercing located through the skin of the navel. It is most commonly located on the upper fold of skin, but can also be affected underneath or around the edges of the navel, according to Wikipedia. Healing takes 6 to 12 months. In jewelry, it's used as barbell or captive bead ring. Its location is on the navel. Niobium uses today. Niobium is used in alloys including stainless steel. It improves the strength of the alloys, particularly at low temperatures. Alloys containing niobium are used in jet engines and rockets, beams and girders for buildings and oil rigs, and oil for gas pipelines. This element also has superconducting properties. It is used in superconducting magnets for particle accelerators, MRI scanners, and NMR equipment. NMR, or nuclear magnetic resonance spectroscopy, most commonly known as NMR spectroscopy or magnetic resonance spectroscopy, is a spectroscopic technique to observe local magnetic fields around atomic nuclei, according to Wikipedia. Niobium oxide compounds are added to glass to increase the refractive index, which allows corrective glasses to be made with thinner lenses. An alloy of this rare metal is used to make wires that provide electricity to very powerful magnets. The magnets in the 16.78 mile, 27 kilometer long Large Hadron Collider, LHC, the world's largest particle accelerator, use 1,323 tons or 1,200 metric tons of niobium alloy. Physicists use this machine to make atoms collide with each other at high speeds. Niobium's atomic mass is 92.906. Its state is a solid. Its discovery was in 1801 by Charles Hatchett, 1844 by Heinrich Rose, and 1864 by Christian Blomstrand. Here we have laboratory refined rods of pure niobium. Here we have the shiny metallic surface. Niobium, element number 41. Symbol NB. Hypoallergenic. Niobium and some of its alloys are hypoallergenic and used in prosthetics, pacemakers, and jewelry. Superconductor. Particle accelerators and MRI scanners use superconducting niobium titanium magnets. Glasses. Niobium oxide increases the refractive index of glass, allowing corrective glasses to have thinner lenses. Niobium is frequently used in body-piercing jewelry because it is inert and can be attractively colored through a simple electrochemical process. Varying the voltage during the process creates different oxide patterns on the surface. Light diffraction by these patterns give rise to different colors. Niobium with a 0 oxidation state is a conductor. Niobium with a +2 oxidation state is also a conductor. Niobium with a +4 oxidation state is an N-type semiconductor, used in transistors or solar panels or other technologies that utilize semiconductors. Up to its +5 state, it is an insulator or dielectric. A dielectric, for example, is used in a capacitor. It can be air, paper, or another type of insulator. In electromagnetism, a dielectric is an electrical insulator that can be polarized by an applied electric field. Niobium is used in the combustion chamber. Superalloys with refractory metals such as tungsten, molybdenum, niobium, and tantalum. Ceramics and ceramic metal mixes. Here we have some information on other elements that exist in different components of the jet. And in the different parts of the turbine, we have different elements. In the exhaust nozzle, we have nickel, iconal, and stainless steel alloys. In the turbine, we have nickel-based superalloys. In the compressor, we have nickel, cobalt, or iron-based alloys. Additives are aluminum and or titanium and chromium, as well as rare earth elements like yttrium. In the fan, we have aluminum, titanium, or stainless steel. In the casing, we have aluminum or polymer matrix materials. Electrical uses. Superconductivity is the total disappearance of electrical resistance below a definite temperature, called the transition temperature. Because niobium has the highest transition temperature, 9.3 Kelvin, negative 264 degrees Celsius, or negative 443 degrees Fahrenheit, among metals, niobium alloys are the most practical choice for superconducting applications. Niobium titanium, niobium zirconium, and niobium tin alloys are indispensable for the application of superconductivity in machinery, magnetically levitated trains, high-energy physics, and magnetic resonance imaging. Transition temperature. Transition temperature is the temperature at which a material changes from one crystal state to another. More formally, it is the temperature at which two crystalline forms of a substance can coexist in equilibrium, according to Wikipedia. What are superconductors? Superconductors are materials which transport electric charge without resistance and with the display of associated macroscopic quantum phenomena such as persistent electrical currents and magnetic flux quantization, according to ScienceDirect.com. What material is a superconductor? Superconductor material classes include chemical elements, e.g., mercury or lead, alloys, such as niobium, titanium, germanium, niobium, and niobium nitride. We're talking about niobium in this video. Ceramics, YbCO, and magnesium diboride, superconducting pinknites, like fluoride-doped LaOFeAs, or organic superconductors, fullerenes, and carbon nanotubes, according to Wikipedia. Why is gold not a superconductor, even though it conducts electricity very well? This is also the reason why good conductors at room temperature, which are close to these in the periodic table, for example, copper, silver, platinum, and gold, do not become superconductors at low temperatures. The interaction between the lattice and the valence electrons are simply too weak, according to chm.bris.ac.uk. Superconductors are used for energy generation, defense, transportation, industrial, medical, and science and research. What is an undulator? An undulator is an insertion device from high-energy physics and usually part of a larger installation, a synchrotron storage ring, or it may be a component of a free electron laser. It consists of a periodic structure of dipole magnets. These can be permanent magnets or superconducting magnets. Here we have some information on niobium, titanium, zirconium, and tin. Niobium, or columbium, is a chemical element with chemical symbol Nb and atomic number 41. It is a light gray, crystalline, and ductile transition metal. Pure niobium has a Mohs hardness rating similar to pure titanium, and it has similar ductility to iron, according to Wikipedia. Corrosion-resistant and high-temperature alloys. A successful development in the conversion of energy was the high-pressure sodium lamp, for which discharge tubes are made of niobium and 1% zirconium. This alloy is chemically resistant to sodium vapor at 800 degrees Celsius or 1,450 degrees Fahrenheit, and it has the same expansion coefficient as the alumina tube to which it is attached, so that the brazed joint between them is quite reliable in service. What is a high-pressure sodium lamp? High-pressure sodium, HPS lamps, are part of the family of high-intensity light bulbs that put out large amounts of light generally needed for street lighting and security lighting. The combination of metals and gases inside of the glass tube produces an orange-white light commonly found in street lights. Here we have high-pressure sodium. Here's how the lighting looks in the parking lot. Looks nice and eerie. And here we have light-emitting diodes. It looks like we've been transported into the future. The material is very ductile at low temperatures. Therefore, by means of a suitable drawing process, the final components can be fabricated to precise tolerances without intermediate heat treatment. Niobium, 1% zirconium, and zirconium, 2.5% niobium, are used in various parts of nuclear reactors. Niobium-based alloys such as WC-103, niobium, 10% hafnium, 1% titanium, WC-129Y, niobium, 10% hafnium, 10% tungsten, and 0.1% yttrium, and CB-752, niobium, 10% tungsten, 2.5% zirconium, are widely used in rocket nozzles and re-entry guides because of their good workability and strengths at elevated temperatures. Chemical compounds. Niobium glass. Optical glasses containing up to 30% niobium pentoxide have high refractive indices, which allow lenses to be much thinner and lighter than ordinary ones. This advantage has led to the wide use of niobium glasses in lenses for cameras, copying machines, eyeglasses, and other optical instruments. Here we have the refractive index formula. N is the refractive index. Refractive index of a medium is the ratio of the speed of light in a vacuum to the speed of light in the medium. Therefore, it has no units. The speed of light is equal to 299,792,458 meters per second. V is the phase velocity of light. The phase velocity is defined as the velocity for a single wavelength wave, whereas the group velocity is defined as the velocity for a packet of waves in which the waves vary in wavelength. Wave velocity is called phase velocity. Waves can be in a group, and such groups are called wave packets. So the velocity with which a wave packet travels is called group velocity. The velocity with which the phase of a wave travels is called phase velocity. The relation between groups of velocity and phase velocity is proportionate. Niobium's refractive index is 2.82677, even higher than that of diamond. Niobium, also known as columbium, is the chemical element with the symbol Nb and the atomic number 41. It is a rare, soft, gray, ductile transition metal. For a typical sample of Nb, the refractive index and extinction coefficient at 632.8 nanometers are 2.82677 and 2.860968, according to filmmetrics.com. So with that logic, phase velocity of light is lower in objects with a higher refractive index. Here we have some information on niobium pentoxide. Niobium pentoxide is the inorganic compound with the formula Nb2O5, a colorless, insoluble, and fairly unreactive solid. It is the most widespread precursor for other compounds and materials containing niobium. Here we have a molecule of niobium pentoxide. Here we can see the 2 atoms of niobium, 1, 2, and the 5 atoms of oxygen, 1, 2, 3, 4, and 5. Here we have the animated 3D model of it. As you can see in 3D, this is how it looks like if you were to rotate it and view it in the 3D space. Again, niobium pentoxide is used to make niobium glass for glasses and for lenses, such as in cameras. Let's continue with the element niobium. Single crystal lithium niobate, a transparent, relatively hard and dense material that resembles clear glass, is particularly suitable for electro-optical applications. The electro-optical effect, also known as the Pockels effect, is an optical phenomenon in which the refractive index of a medium varies linearly with an applied electric field. Electro-optical modulators are used for modulating or encoding information on laser beams in laser communication systems. A piezoelectric transducer is a device that produces an acoustic wave from a radio frequency, RF input, or, conversely, converts an acoustic wave to an RF output. Single crystals of lithium niobate are particularly suitable for these applications because they exhibit large electromechanical coupling factors, have low high-frequency losses, and can convert electrical energy to acoustic waves with efficiency. Here we have a molecule of lithium niobate consisting of niobium in the center, lithium here, 1, 2, 3 atoms of oxygen. Niobate transducers are used in radar, communication systems, and television receivers. Lithium niobate is a non-naturally occurring salt consisting of niobium, lithium, and oxygen. If you're interested in learning about lithium and oxygen, I can leave a link in the description below. I have made a video on those elements. Its single crystals are an important material for optical waveguides, mobile phones, piezoelectric sensors, optical modulators, and various other linear and nonlinear optical applications. Its formula is LiNbO3. What are radio crystals used for? The crystal functions as an envelope detector, rectifying the alternating current radio signal to a pulsating direct current, the peaks of which trace out the audio signal so it can be converted to sound by the earphone, which is connected to the detector. A television set or television receiver, more commonly called the television, TV, TV set, telly, or tube, is a device that combines a tuner display and loudspeakers for the purpose of viewing and hearing television broadcasts, or using it as a computer monitor, according to Wikipedia. I'm currently using a television as a computer monitor as we speak to record this video and read off the script. Pockels effect. The Pockels effect, or Pockels electro-optic effect, named after Friedrich Karl Alwin Pockels, changes or produces birefringence in an optical medium induced by an electric field. In the Pockels effect, also known as the linear electro-optical effect, the birefringence is proportional to the electric field, according to Wikipedia. Piezoelectricity is the electric charge that accumulates in certain solid materials, such as crystals, certain ceramics, in biological matter such as bone, DNA, and various proteins in response to applied mechanical stress. The word piezoelectricity means electricity resulting from pressure and latent heat, according to Wikipedia. PTZ is made from lead zirconate titaniate and can produce more voltage than quartz with the same amount of mechanical pressure. Here we have the piezoelectric crystal, and that produces the spark, along with the gas, ignites the flame. Piezoelectricity. Niobium is also used as an optical transmitter and an optical receiver. The infrared light used for laser communications differs from radio waves because the infrared light packs the data into significantly tighter waves, meaning ground stations can receive more data at once. While laser communications aren't necessarily faster, more data can be transmitted in one downlink, according to nasa.gov. Niobium Nb has a body-centered cubic BCC crystal structure and a melting point of 2,468 degrees Celsius, or 4,474 degrees Fahrenheit, according to Britannica.com. Of the refractory metals, it has the lowest density and best workability. For this reason, niobium-based alloys are often used in aerospace applications. Because of its strengthening effect at elevated temperatures, its principal commercial use is as an additive in steels and superalloys. Niobium titanium and niobium tin alloys are used as superconducting materials. Niobium history. When examining minerals in the British Museum in 1801, Charles Hatchett was intrigued by a specimen labeled columbite. He suspected it contained a new metal, and he was right. He heated a sample with potassium carbonate, 2 atoms of potassium, 1 atom of carbon, and 3 atoms of oxygen. Dissolved the product in water, H2O, added acid, and got a precipitate. Here introduced columbite. Columbite, also called niobate, niobate tantalite, and columbate, Nb2O6, is a black mineral group that is an ore of niobium. It has a submetallic luster and a high density and is a niobate of iron and manganese. This mineral group was first found in Haddam, Connecticut in the United States, according to Wikipedia. Its color is black or brownish black. Its cleavage is distinct. Its streak is blackish brown. On the Mohs scale of hardness, it's a 6. Its luster is submetallic. Its fracture is subconchoidal. Fractures developed in brittle materials characterized by semi-curving surfaces. Its category is oxide minerals because it's an oxide of niobium. However, further treatment did not produce the element itself, although he named it columbium, so it was known for many years. Here we have some information on Charles Hatchett. He was a British chemist. Charles Hatchett, FRS, FRSE, was a British mineralogist and analytical chemist who discovered the element niobium, for which he proposed the name columbium. Hatchett was elected a Fellow of the Linnean Society in 1795 and of the Royal Society in 1797, according to Wikipedia. Others doubted columbium, especially after the discovery of tantalum, which happened the following year, 1802. These metals occur together in nature and are difficult to separate. In 1844, the German chemist Heinrich Rose proved that columbite contained both elements, and he renamed columbium niobium. A sample of the pure metal was produced in 1864. Here we have maps of 1864, Europe, Asia, South America, and North America. It was during the Civil War. A sample of the pure metal was produced in 1864 by Christian Blomstrand, who reduced niobium chloride by heating it with hydrogen gas. Here we have the unbalanced imbalance formula. So in this formula, we have H2O. It's essentially rusty hydrogen. And here we have a similar formula, except it's unoxidized hydrogen, not rusty hydrogen, to produce NbHCl. This is the formula that Christian Blomstrand tested. Christian Wilhelm Blomstrand was a Swedish mineralogist and chemist. He was a professor at the University of Lund from 1862 to 1895, where he isolated the element niobium in 1864. He developed an early version of the periodic table and made advances in understanding the chemistry of coordination compounds, according to Wikipedia. Due to the great chemical similarity of niobium and tantalum, the establishment of the individual identities of the two elements was very difficult. Niobium was first discovered in 1801 in an ore sample from Connecticut by the English chemist Charles Hatchett, who called the element columbium in honor of the country of its origin, Columbia, being a synonym for the United States. In 1844, a German chemist, Heinrich Rose, discovered what he considered to be a new element, occurring along with tantalum, and named it niobium after Niobe, the mythological goddess who was the daughter of Tantalus. After considerable controversy, it was decided that columbium and niobium were the same element. Eventually, international agreement about 1950 was reached to adopt the name niobium, though columbium persisted in the U.S. metallurgical industry. Niobium was discovered in 1801 by an English chemist, Charles Hatchett. Since Hatchett's mineral sample came from New England, he named it columbium, CB, after Columbia, another name for America. In 1844, Heinrich Rose, a German chemist, announced his discovery of an element that he named niobium, after Niobe, the mythical daughter of Tantalus, who in turn gave his name to tantalum, with which niobium is often associated in minerals. Niobium was later proved to be the same element as columbium, and niobium was accepted as the official name by the International Union of Pure and Applied Chemistry in 1950. In 1905, W. von Bolton, a German chemist, succeeded in producing niobium in a pure ductile state. Niobium was first added to tool steels around 1925 and was first used to stabilize austenitic stainless steel in 1933. Interest in adding niobium to high-strength, low-alloy HSLA steel can be traced to the work in 1939 of F.M. Beckett and R. Franks, who demonstrated that niobium strengthening reduced reliance on conventional hardeners such as carbon, manganese, chromium, and molybdenum, thereby improving weldability. In 1958, Norman F. Tisdale of Molybdenum Corporation of America added 0.01 through 0.034% niobium to carbon steel as a grain refiner for improving toughness. The development of niobium-based alloys for aerospace application began in the late 1950s. Here's a map of the 1950s. Here's a map of 1950 CE. Again, a quick summary. Charles Hatchett discovered niobium in 1801. Its origin of name: the name comes from Niobe, from Greek mythology, who was the daughter of King Tantalus. This was chosen because of niobium's chemical similarity to tantalum. Its classification is a metal. Niobium is roughly 10 times more abundant in the crust of the earth than is tantalum. Niobium, more plentiful than lead and less abundant than copper in the earth's crust, occurs dispersed except for relatively few minerals. Of these minerals, the columbite tantalite series, in which columbite FeNB2O6 and tantalite FeTA2O6 occurs in highly variable ratios, is the main commercial source. Pyrochlorate, a calcium-sodium niobate, is also the principal commercial source. Natural niobium occurs entirely as the stable isotope niobium-93. Here we have niobium-93. Its atomic mass is 92.906. Its natural abundance is 100%. Its half-life and mode of decay are not included because it is stable. Its common oxidation states are +5 and +3, which means that its most common states are 5 lost electrons or 3 lost electrons. The production procedures for niobium are complex, the major problem being its separation from tantalum. Separation from tantalum, when necessary, is effected by solvent extraction in a liquid-liquid process. The niobium is then precipitated and roasted to niobium pentoxide, which is reduced to niobium powder through metallothermic and hydriding processes. Here we have niobium pentoxide. Niobium pentoxide is the inorganic compound with the formula Nb2O5. Niobium can also be obtained by either electrolysis of fused salts or reduction of fluorocomplexes with a very reactive metal such as sodium. The pure metal is soft and ductile. It looks like steel or, when polished, like platinum. Although it has excellent corrosion resistance, niobium is susceptible to oxidation above about 400 degrees Celsius or 750 degrees Fahrenheit. Niobium can best be dissolved in a mixture of nitric and hydrofluoric acids. Completely miscible with iron, it is added in the form of ferroniobium to some stainless steels to give stability on welding and heating. Niobium is used as a major alloying element in nickel-based superalloys and as a minor but important additive to high-strength, low-alloy steels. Because of its compatibility with uranium, resistance to corrosion by molten alkali metal coolants, and low-temperature neutron cross-section, it has been used alone or alloyed with zirconium in claddings for nuclear reactor cores. Cemented carbides are used as hot pressing dies, and cutting tools are made harder and more resistant to shock and erosion by the presence of niobium. Niobium is useful in construction cryogenic, low-temperature electronic devices of low power consumption. Niobium tin Nb3Sn is a superconductor below 18.45 kelvins K, and niobium metal itself below 9.15 K. Niobium carbide is an extremely hard refractory ceramic material commercially used in tool bits for cutting tools. It is usually processed by sintering and is a frequent additive as grain growth inhibitor in cemented carbides. It is the appearance of a brown-gray metallic powder with purple luster. According to Wikipedia, compounds of niobium are of relatively minor importance. Those found in nature have the +5 oxidation state, but compounds of lower oxidation states, +2 to +4, have been prepared. Quadruply charged niobium, for example, in the form of carbide, NBC, is used for making cemented carbides. Here we have the main differences between conductors and superconductors. Characteristics. Definition. A conductor. An object or material that allows the flow of charge when applied with a voltage. A superconductor. It is a conductor that has zero electrical resistance and expels magnetic fields. Characteristics. Electrical resistivity. Normal conductors have some resistance that depends on its length, width, and material. Superconductor. Superconductors have no electrical resistance below critical temperatures. Energy consumption. Conductor. Due to its resistance, the conductor consumes energy in the form of heat. Superconductor. There is no energy loss or consumption in superconductors. Current storage. Conductor. The current in a conductor die out when the power source is removed. Superconductor. The current in superconductor keeps flowing even after the source is removed. Magnetic field. Conductor. The magnetic field lines of force pass within the conductor. Superconductor. The superconductor expels a magnetic field from the inside. Quantum locking or levitation. Conductor. A simple conductor does not have such a feat. Superconductor. The quantum locking is a state in which the superconductor stays locked, hovering in a magnetic field. Energy storage. Conductor. A conductor cannot store energy due to its resistance. It dissipates energy. Superconductor. A superconductor does not dissipate energy, so it can store energy. Power transmission. Conductor. You need multiple conductors with huge gauges to transfer power between stations. Superconductor. A single superconductor can transmit power between stations without any loss or insulation burnout. Operating temperature. Conductor. Conductors can operate in normal range of temperatures. Superconductor. These conductors achieve superconductivity when it is supercooled down below 5 Kelvin. Limitation. Conductor. Conductors have specific current ratings and they cannot withstand heavy current. Superconductor. The superconductors can tolerate an infinite amount of current, but its temperature needs to be below the critical temperature. Applications. Conductor. The conductors are made into wires for conduction of electrical current. Superconductor. The superconductors have no efficient application to date due to its very low temperature, but it will revolutionize our life once its temperature is maintained efficiently. Extraction and refining. Ferroniobium. Pyrochlorate concentrates are commonly reduced to ferroniobium through an aluminothermic process. In this process, the concentrate is mixed with hematite, an iron ore, aluminum powder, and small quantities of fluorspar and lime fluxes in a rotary mixer and then unloaded into steel containers lined with magnesite refractory bricks. Here the charge is placed in circular concave pits made of a mixture of lime, fluorspar, and silica sand, and reduction is initiated by the ignition of a mixture of aluminum powder and sodium chlorate or barium peroxide. The exothermic reaction lasts about 15 to 30 minutes, and the temperature reaches about 2,400 degrees Celsius or 4,350 degrees Fahrenheit. Most of the gangue impurities from the concentrate, including all the thorium and uranium oxides, enter the molten slag. When the reaction is finished, the slag is tapped off and the vessel is lifted, leaving the material to solidify in the sand. The ferroniobium alloy is then crushed to particle sizes of 10 millimeters, about 3/8 of an inch, for marketing. The content of this alloy is 62 to 69% niobium, 29 to 30% iron, 2% silicon, and 1 to 3% aluminum. Identifying minerals. With experience, many minerals can be identified by their appearance and texture alone. Important clues include their color, their luster, the way light reflects from their surface, and above all, their habit or crystal form. Crystals are grouped into 6 systems according to their symmetry. In addition, the crystals themselves can be arranged in different ways. Many are parallel, but they can be dendritic, branching, or even botryoidal, like a bunch of grapes. Minerals also differ in density or specific gravity, Sg, measured by comparing the weight of a mineral to that of an equal volume of water, and in their hardness, H. On the 10-point Mohs scale, which measures hardness, talc is rated 1, whereas diamond, the hardest mineral, is rated 10. A fingernail, hardness 2, copper coin 3.5, and steel knife blade 6 all make useful benchmarks for testing hardness. Surprisingly, size is a less useful clue. Gypsum crystals, for example, are usually less than 3/8 inch or 1 centimeter long, but the largest specimens ever discovered are the size of a 2-story house. Cubic systems are common and easily recognized. Such crystals have 3 axes or right angles. Shapes include the cube and the 8-faced octahedron. Hexagonal and triagonal systems are very similar to each other with 4 axes of symmetry. Their crystals are often 6-sided prisms with pyramidal tops, seen on the left. Tetragonal. Tetragonal systems have 3 axes of symmetry, all at right angles and 2 of equal length. In a tall prism, left, the vertical axis is longer. Squat prisms are also common. Monoclinic. Monoclinic systems have 3 unequal axes of symmetry, only 2 at right angles. Tabular, flattened left, and prismatic habits are common. Orthorhombic. Orthorhombic systems are similar to the monoclinic system, but all 3 axes are at right angles. The usual habits are tabular and prismatic, seen on the left. Triclinic. Triclinic systems have a low degree of symmetry because the 3 axes are unequal in length and none of them are at right angles. Prismatic habits are common. Niobium is a body-centered cubic, which is why the crystals seen in this image are cubic. Niobium powder. Columbite concentrates and tin slags with a high tantalum content greater than 10% are directly dressed in most cases by a wet chemical process. Low tantalum tin slags, on the other hand, are first melted in an electric arc furnace with the addition of a flux material, and the tantalum niobium content is collected as a ferroalloy. The tantalum-rich ore or ferroalloy is then crushed, ground, and decomposed in hydrofluoric acid. This is followed by a liquid-liquid extraction process, in which 2 metals are dissolved in a slightly acidic aqueous feed solution into which an organic solvent, usually methyl isobutyl ketone, is mixed. The tantalum is extracted as a fluoride in the organic solution, while niobium remains in the aqueous residue or raffinate. The niobium is then precipitated from solution as a fluoride by the addition of ammonium hydroxide, and the filter cake is dried and roasted or calcined at 900 through 1000 degrees Celsius or 1650 to 1800 degrees Fahrenheit to obtain niobium pentoxide. The oxide may be reduced aluminothermically to produce niobium reguli, impure metallic globules, as in the production of ferroniobium. The reguli may be further purified by electron beam melting into ingots, or they may be put through a hydriding or dehydriding process to produce niobium powder. In the hydriding process, the impure niobium is crushed into chunks and placed in a furnace, which is evacuated and heated to 800 degrees to 950 degrees Celsius, or 1450 to 1750 degrees Fahrenheit. After hydriding, the niobium is crushed and pulverized to fine powder, which is then reheated and dehydrated in a vacuum to produce niobium powder. The powder can be pressed with a mechanical or isostatic press into green, that is, unfired compacts with a density of 60 to 65% of the theoretical maximum, and then sintered. Sintering is then carried out in a vacuum at 2100 to 2300 degrees Celsius, or 3800 to 4150 degrees Fahrenheit, either by direct resistance heating or by indirect heating. When direct resistance is applied, electrical contact is made via water-cooled copper clamps with brazed tungsten facings. The temperature is increased in stages to permit the evaporation of impurities and to prevent the sudden release of gas. During vacuum sintering, a purification of the metals takes place, leading to an improvement of its mechanical properties. Demands in the construction, transportation, and energy industries for stronger, tougher, more formable, and more weldable steel brought the development of the family of HSLA steels. As noted previously, the addition of niobium to these steels gives rise to the improved properties while allowing a decreased use of carbon and manganese. Also, when niobium exceeds its solubility limit in the steel matrix, it precipitates as a carbide or nitride. Here we have niobium carbide, here we have niobium nitride, acting as a grain refiner and further improving the toughness and strength of the steel. The addition of niobium to stainless steel generally forms carbide precipitates, which bring about a dispersion hardening effect in the matrix. At the same time, it prevents the formation of chromium carbide, which would have a detrimental embrittling effect on the material. Many grades of martensitic stainless steels contain niobium for refinement of the grain size, thereby improving creep resistance and toughness. Ferritic stainless steels also use niobium for the stabilization of interstitial impurities such as carbon and oxygen in order to avoid intergranular corrosion. The main source of this element is the mineral columbite. The mineral also contains tantalum, and the two elements are mined together. Columbite is found in Canada, Brazil, Australia, Nigeria, and elsewhere. Some niobium is also produced as a byproduct of tin extraction. Niobium occurs mostly as an oxide and has a strong geochemical coherence with tantalum. Major minerals of niobium are pyrochlorite, NaCa2, Nb2O6F, and columbite, FeMn, NbTA, and 2O6, consisting of niobate, tantalate, iron, and manganese. Pyrochlorite occurs usually in carbonatites and in pegmatite, derived from alkalic rocks, commonly in association with zirconium, titanium, thorium, uranium, and rare earth minerals. Columbite is normally found in intrusive pegmatite and biotite in alkalic granites. However, since most such deposits are small and erratically distributed, they are usually mined as a byproduct of other metals. There are large pyrochlorite mines in the Brazilian states of Minas Gerais and Goiás, and at Saint Honoré, Quebec, Canada. Large columbite deposits are found in Nigeria and Congo, Kinshasa. Also, columbite concentrates are obtained as byproducts of tin mining in Nigeria. Because of the altered and decomposed nature of overburden and ore materials, the Brazilian deposits are mined by the open pit method. The ore is generally divided into blocks and processed by ripping, bulldozing, loading, and transporting. Mining in Quebec follows underground methods. What is ripping in mining? Ripping is a method of loosening a soil or rock before the final excavation. Today, most of the mining class bulldozers are equipped with a giant ripper or multiple rippers. Ripping with a dozer has become a popular method to loosen soil when blasting can be avoided as extremely expensive, according to LinkedIn.com. Crushing is the process of size reduction of ore. Size reduction process begins with usage of explosives at the area for production of ore. In later stages, the size reduction process performed with crushers before grinding in mills is called crushing, according to mechaglobal.com. Concentration of ore is accomplished by crushing and grinding, magnetic separation to remove magnetite, and then desliming and flotation separation. The term slimes is used everywhere in mineral processing, but the definition in relation to particle size distribution in mineralogy seems to vary depending on the mineral being mined and who is talking about it. As the name suggests, Slimes consist of the fine solids fraction of slurries, according to alfavel.com. So that was niobium explained in X minutes or less and as a short amount of time as possible. Once again, if you liked this video, make sure to like, comment, and subscribe. Other than that, thank you everyone for watching. Have a great one.